if you have any questions to Michele, please put them as always in the chat box and we'll take them one by one. So Michele, over to you.
Yeah, thank you, Jousef, for your kind introduction, and good evening to everyone. I'm sorry I cannot be seen right now. I don't have a camera, but I hope I can keep your interest to the point where you just need to look at the slides. So yeah, as Jousef mentioned, today we talk about a meshless CFD approach. It's a novel approach, a very recent approach. That is, so the software is called the Particleworks, and it's based on what is known as moving particle simulation. So yeah, it's a particle-based fluidodynamics, computational fluidodynamics simulation tool. We will explain a little bit of the feature in the first slide. Here we have an agenda of today, of my talk today. So we will do a little bit of introduction first, but then we look at why we need to study e-motor cooling and why this software is used in e-motor cooling. Actually, I have a couple of examples from industrial collaborations we have. And then I will briefly show you the software and do a little demo, actually, of the software, just to give you an overview of how the graphic user interface is. And at the end, I will also discuss, as this is the code week, I will discuss how to automate some part, actually the entire simulation workflow with Python and an API that was developed for the software, okay? So briefly presenting myself and my company. So Particleworks is sold in Europe by this headquarter that is in the north of Italy. We are Particleworks Europe, and we coordinate different reseller or across Europe, so Germany, France, Spain, and so on. So we really try to combine the know-how on the software, but also the know-how in the industrial application and validations, okay? So we really try to collaborate, and we will see some examples with important companies to have a simulation tool that is easily usable, but also that provides the answers that industries need, okay? So we do a little bit of both, consulting, servicing, and also reselling the software, Particleworks. The moving particle simulation is based on this Lagrangian formulation. So as I mentioned, it's also Jousef mentioned it in the introduction. Particleworks is a meshless approach. So contrary to the conventional methodology, we don't have to prepare the geometry or prepare a static mesh, an Eulerian mesh, but actually the software will automatically create particles, and those will be the computational nodes on which we compute the usual Navier-Stokes and continuity equation. It's interesting to notice that the methodology was proposed by a professor in Japan, Professor Kushizuka, and he is also founder of the software house that is behind Particleworks. So we have an example of, let's say, a software that was developed in the academic world, but then it was widely applied, and it's widely applied in industry. So a little bit of, again, side-by-side comparison as compared to the conventional method, finite volume method, like Fluent or Star CCM. We don't have to mesh the entire domain, but actually the mesh is localized where the fluid is, okay? And then we can follow along the solution, the splashing, the droplets formation as well. So it's very easy to set up a simulation, and it's very suitable whenever this kind of simulation, whenever we have splashing phenomena or jets, this kind of free surface flow, okay? Because to deal with the droplet and this kind of phenomena with the finite volume, it's very challenging, Okay. Here is an example of the application of the software. We have multiple examples in the automotive sector for lubrication of gearboxes, for cooling of e-motor. Also, here we have an example of grease. So grease that lubricates bearing, piston cooling, axles, and also this kind of wading type of simulation where we have an entire car body that interacts with some water amount, and we might want to look at the contamination inside the car body and so on. So deal with something like this with a mesh-based approach, it will be basically impossible. And I want to also mention that here we are doing a coupled aerodynamic. Sorry, I have problems. Sorry, my PPT just crashed.
Windows problems, Michele, no problem.
Okay. Sorry about that. So we were here. Yeah, I was just mentioning that you can look inside the body, and it's also the fluid is interacting with the car, and it's lifting the car. So this is a very complex type of simulation that is very challenging with finite volume method. It doesn't seem to like that video, so it's crashing again, I think. Sorry about that. Sorry about that. I will not replay that video, I promise. Okay, so moving towards the electric motor side now. Why do we need the simulation of e-motor cooling, and why we see that it's increasingly requested by the industry? Yeah, of course, we all know that sales in the EV sector is going fast, and we could say that we are approaching the 10% sales over the entire let's say automotive sector. So 10% is electric vehicles right now. So we are approaching a very important let's say phase of the transition, and at the same time the projection for the current the power densities that the e-motor will need to satisfy the efficiencies and the also overall the life cycle requirement of the e-motor will need some more power density. Okay, so moving from 2.5 kilowatt per kilo going to 9 kilowatt per kilo. So it's a lot of heat that needs to be removed, and conventional let's say cooling method like water jackets around the stator are not enough. So Particleworks is used because a new type of cooling system is applied. Actually, sorry, I will just go back to this slide. This is an example of the new cooling system. We have oil jets instead of a water jacket around the stator. We have direct oil jets that impinge on the windings and on the most critical areas. So in this way, we have better cooling efficiencies. Okay, so that is why, since we are dealing with jets, that is why we use Particleworks in this kind of simulation. As I mentioned, the features are that we work directly with the CAD. We don't have to prepare it to simplify the CAD. So we import it directly, and actually the methodology can take benefit of graphic cards to accelerate the computational times. And in this way, we achieve an analysis that takes only days instead of weeks. So we can have a digital prototype that can guide us in the design phase. So we don't have to wait for a physical prototype. That's the objective of the simulation. Yeah, in terms of the output that you can get from this methodology is oil flow distribution inside the distributing channels. Of course, the temperature distribution in the e-motor, that is very important because a lot of materials in e-motor, like magnets, will be affected by the temperature, and we have to control the temperature quite strongly. We can look at contamination of oil in the air gap, so between the stator and the rotor. There can be some oil contamination, and that can cause some losses, power losses. We can improve overall the design and investigate the number of jets, the direction of jets. So there are a lot of things that can be done, of course. Here, a little bit of the overview of the entire simulation. Okay, so what we can do actually is to work on the motor design. So we can look at the electromagnetic part. We can do the 3D analysis on the electromagnetic losses. But then Particleworks really starts to be important here. It takes the model from the 3D electromagnetic, and it does the air simulation to account for windage effects. So of course also air will impact the oil distribution. And then there is the oil jets simulation. And at the end, the objective here is to extract an HTC map. So we project on the walls the cooling effect of oil, and we transfer that map to the finite volume method solver to estimate the temperature in the e-motor. Okay, so you see from start to finish what is like to integrate Particleworks in the e-motor design. So we wanted to also validate that methodology, and we did it with Ricardo, this company that does software in the in many fields, automotive fields, and one for sure is electric motor field. So we took one e-motor from there. It was already shown here. You see the distributing channel inside the e-motor, and then so we had to evaluate the flow distribution here, and then we have the visualization of the flow inside the e-motor with the nozzle spreading oil. Then we did the HTC map, as I mentioned. So we plotted the HTC, the heat transfer coefficient, on the internal walls, the windings, the coils. And then we transfer those to an FEA solver, okay, that can give us the temperature distribution. But it was not enough. We wanted to investigate if this methodology could correlate well with experimental values, okay? So they had some experimental observation. They actually had thermocouples on the coils, and they wanted to have, the objective was to have a max difference of 5 degrees between what was measured and what was simulated. The difference was actually in the range of plus minus 2.8 degrees. So they were very happy because across all the thermocouples, we could have good correlations. So here we really see an example of the simulation applied to a real life example, with also validation of the methodology with experimental result. And it's what we as EngineSoft at Particleworks Europe care the most, okay? So to really have solutions that can give real life answers. Another collaboration we had and we published about is with Nidec PSA. So this one is a joint venture between the PSA group, so Peugeot Citroën group, and Nidec. So yeah, just briefly, I don't want to show every detail here, but they had a similar system, an e-motor, and they had to analyze the cooling circuits, and then they wanted to have some further validation in the flow split actually inside the circuit. So the circuit here is shown will go towards two channels, one in the rotor rotating and one external cooling. So we have here some jets going to the upper region. And they wanted to understand what was the flow split between the two at a different operating point or different RPM for the rotor. And they could see a good correlation between, again, the experimental results and the predicted flow rate distribution by MPS. And what they also did was to modify a geometrical feature like this element in gray here that could have a different channel to direct or redirect the flow in specific ways. Okay, so oil coming from the shaft will go through these channels in the gray region and could be redirected to improve the cooling efficiency of the jets. So because of the ease of use of the software and the ability to change the geometrical feature quite efficiently without having to remesh, for instance, they could see 10+ designs in a matter of days. So here is a little bit of an overview of the publications we have and the available material. Feel free to check them out through these links or on our website that is particleworkseurope.com. So here is the further publications. We have one also with Total Energy. They looked at the oil properties, improving oil properties to have better cooling. Okay, so before discussing the coding capabilities and the possibilities, I would like to show with you the software for a moment. Okay. The graphic user interface, also to give you an overview of how easy it is to set up a case and in general, what is the typical workflow, okay? So I don't want to, let's say, define everything right now. I just will give you through the areas of the GUI, the graphic user interface, that are the most important. But I don't want to type every number like inflow position manually right now, or the physical properties of fluid. So, okay, let's say we create a new project. I could create a new project, and then I will have this project with a set of simulations here. With different, for instance, physical properties. This is a 10 centistokes oil. So, yeah, a specific viscosity, kinematic viscosity. Okay, so what I need to do is to define the inflows. Okay, I already prepared them. I can click here and define an inflow. And then in the properties tab here, I can change the properties of the inflow and set the volumetric flow rate. Okay. As you can see, we have 6 inflows that are close to the coils. This is a geometry that I imported as is. It's an STL geometry that I prepared by exporting the CAD as it was, okay? So I just drag the geometry in and I just change the coloring, but that's it. So to import another shape, I could click here, and again, I can import the casing, some cages. So there are some geometrical features that I import here. Let's hide for a moment the casing. We have here the stator. I can control the alpha, so the transparency of the stator here. As you can see, we don't have a very good resolution, but that's not a problem in the mesh because the software will actually remesh automatically or create a grid around the solid with a specified grid interval. So even if here we see that, yeah, perhaps the resolution of this STL it's not ideal, that is not going to be a problem. The iterations that we did, the number of iterations, the number of particles that are generated, the delta T that was used, the simulated time, and how much it took, physical time, hardware time, to simulate that simulated time. And then a bunch of information about estimated times for the simulation and so on. So while the simulation is running, I could inspect actually the results. And I have a simulation that ran for a little bit longer. So this is the type of output that you can have during in live. So you can really see your results. You see the rotor. You see droplets accumulating at the bottom here. Okay. And you can start to do some post-processing once the simulation is stabilized. Maybe we want to look at the average HTC in the windings area. Maybe we want to take a look at the flow rate distribution or the accumulation of oil in some other areas.
Nice. Michele, we had one question on CAD files. Which formats are supported in terms of CAD?
So we support STL file or OBJ files. Usually STL, the surface triangular files are generated by most of the CADs. Yes.
Got it. With another question, how is the meshless approach interpolating compared to the more typical or well-known finite element approach or finite volume approach? Yeah,
for that, I think we can address that question in the actually week where we look at the methodology in detail on the theory.
Yeah, true.
Right?
Good.
I forgot when I used the session there. But yeah, so in terms of, maybe we can find the information on that session, but in terms of interpolation, of course, here we are dealing with a discrete approach, and particles are interpolated with inside a sphere of influence. So the methodology, the algorithm, will look at a specific particle, and of course the surrounding is discrete. It's not a continuous surrounding in terms of mesh. So it will take the distance between particles, and it will use discretized gradients operator. So in the discretized form, but it will do actually what a finite volume method does. It's just focusing in a specific sphere of influence around every one of the particles. Yeah, it's a little bit difficult to explain maybe now. Does that answer a little bit the question? Or?
Just a quick question. What again, for the layman in me, but it's so fascinating that this would resemble the real world. But I guess every particle, the more particles you add, the more equations you run,
yeah,
the more likely it'll resemble. But are you telling me that if I physically created this product and I had these jets or these holes, and this actually would resemble the real world, right? That's basically what's going on. Yeah, it's amazing, isn't it?
Yeah. So
without any external conditions like wind and vibration, excluding those things, I suppose.
Mm-hmm. I hope I can show you another examples. Yeah. So this one is one of the first application we had from Comer Industries. So here is a clear casing, and here is the gearbox that they simulated. Okay. So I don't know why the video will tilt there. Yeah, it's tilting. So, but just to give you an overview, you can see here that maybe you can see it. I hope you can see it. So you can see the film formation here, and it's very similar to this kind of film formation. You can see that there is an area without oil. That is what is seen also here. So really the results outputted here are what will look like in reality. So that's why we say that is a digital prototyping. Also in the bearings area, you see that there is a good correlation in the, okay, this video should be moved a little bit. You see here, sorry about the fact that it's tilting. But so they did actually some correlations between the lubrication at different clock speed, different load cases, and they could correlate the simulation with test in terms of oil amount or estimated oil amount in bearings area or so on. Okay.
Thank you. Interesting.
Yeah. Any other question or curiosity?
I think we had one. To what percentage does this resemble reality? If that's possible to put a figure on.
Yeah, as I mentioned, the correlation is there in terms of temperature prediction, because at the end you want to have a temperature prediction. And the temperature prediction that we got with Ricardo were very good. As I mentioned, in the range, way in the range of what they require. So 2 or 3 degrees of difference between measured and simulated results. I would say it's quite good actually. Yeah, also the visualization of it, it's quite similar. If you want to have a look at more examples in that regard, you can take a look also at the FEV example. In here they have a clear casing for the e-motor with the oil accumulating around, and you can have a comparison between the two. So please check out this paper. Okay, what I would do then here, let's say I saw that the stabilization, so the number of particles is not increasing anymore, so meaning that the oil that accumulates stabilized. Once I get there, I could run some post-processing. One is the mapping post-processing that will project actually the HTC of oil onto a specific element, like perhaps the coils. So I can import the coils, that is the STL of the coils. I can do a map of the HTC, transfer coefficient of the coils. I could do it maybe for a specific frame, or do an average, whatever. I could have a CSV output. And once we have that, if we go to the color map, heat transfer coefficient, we might want to hide for a moment the STL and also the inflow here. I hope I applied actually the boundary condition correctly. I don't think I did. So we don't see the heat transfer coefficient actually on that. Let's see if I can solve for that. Sorry about that. So let's see, perhaps this one, case gear. I might add a problem on the way I define some boundary conditions. So actually, right now I'm not getting maybe in this simulation, I'm not getting the correct the correct HTC. So I'm sorry about that. I don't have an example. But the idea is that here we would see the HTC of oil in the impinging area, like we see in this case here. Okay. Yeah. Any more questions? So here is just an overview of how the software looks like and how our workflow is usually built. So it's very nice because it's easy to set up, but it's also easy to use. As you can see, that there are not 100 windows or 3 interfaces for pre-processing or post-processing. Everything is done in this graphic user interface. For the post-processing, the, let's say, surface rendering maybe, so to render the fluid in a nice way. I could do various type of post-processing, but we don't have really time to go through them right now. But this is the overview. Okay, I wanted to give you. Let's briefly discuss about the automation aspect. So the developer of the software actually built an API to control your simulation, the simulation in Particleworks with Python. So I built a case, for instance, here from scratch only with code. In here, as you can see, I can define the DT, the particle size. I can check or uncheck some pre-processing or post-processing conditions. And then I can define all the parameters actually of the simulation. I will give you an overview of the steps that, so how to build every part of the simulation with the code. Here is just an overview of the requirements in terms of Python requirements. So we are looking at 3.8, actually, version 3.8 for Python. And here is what you can do. We can do the creation of the scene, the setup of the simulation. We can do a parametric screening of our simulation, maybe changing the particle size or some other physical properties. Maybe you can do a screening of the oil physical properties. You can launch pre-processing, but also post-processing. And here is an example of some sort of automation of the post-processing that can be done in Particleworks. As I mentioned, I built this case on the right, just using the code. As you can see, we have a certain particle size defined here, particle size 1.5 e minus 3. We have all the objects, and actually, as you can see here, we have different dictionaries, Python dictionaries, to define the objects, to define the rotational speeds of the objects, to also define with other dictionaries, the oil dictionary here. We could define the physical properties of oil, and so on. So running this script will result in what you see on the right, from anything, starting from nothing, okay? So I just wanted to include here a couple of examples of the code for every step. Here is just to set up the environment, okay, and to import the module, the PVPy module. So you have a reference in case you will try. This one is the function to create a project, a new project, if it's not already there. Otherwise, it's overwritten, I think, actually. And then you can create a certain scene, also a certain simulation, given the D size, so the particle size. So this script will rename the scene with the given D size. And then in this case, we actually imported an STL. We created a node given that STL. And we applied, we rename we give the object a name, and we read the STL actually. This one is to define the object from the STL. You can move the object, and you can apply a certain physical property, changing also some details of the boundary condition. In this case, the double-sided DF option was activated on that element. It's an advanced settings, but it's just showing you how you can, from a dictionary, again, call, using this key, you can define the property of that object, like the physical, the double-sided DF. Then you do the animation. So you set maybe the rotations. And you can also apply an animation script to the object. So yeah, very advanced type of scripting we see here. So I don't want you to understand everything. Of course, it's impossible right now. But I just want to give you some examples of how you handle the GUI settings with the script. Is there a new question?
There's one question. What are the main benefits to connecting the Python code to Particleworks? Speed of doing many tests, machine learning?
Actually, no. The simulation time here is usually the bottleneck. So you cannot really run 95% of the time. You cannot run, let's say, 20 simulation in a day or in a sec or in 10 minutes. We do have actually optimization examples for very simple simulations for now, using Mod Frontier. So Mod Frontier is an optimizer, and you can automate the launch and the post-processing with the Python interface to test, for instance, different inflow location for lubrication purposes. Let's say you have a gear and you have an inflow close to the gear. You want to test 100 position of the gear of the inflow. You can do some machine learning or some optimization thanks to the optimizer that is Mod Frontier in this case, and the automation you enable with the Python. Okay.
Great. Yeah.
So here is how you define the fluid. You create a fluid and you change the density. As you can see, it's very easy because every key is self-explanatory, and you change the properties, physical properties. You define the emit mode, emit rate of the inflow. So you basically create a node, and you change the properties of that node. And you apply the material with the fluid that you define. And then, here is check actually the simulation domain. It's a for loop to adapt the domain. So to check actually the domain, to find the domain. So this part of the code will loop through the nodes, and it will find the domain, and it will adjust the dimension of the domain. Okay, so yeah, I just wanted to say that every key here is represented by a properties found in the sub.json. This is a file that is inside the directory of your simulation, and it collects all the information that describe your simulation. Okay. So if you don't know what key here you have to call, you can likely check the sub.json. And running processing simulation, pre-processing simulation. Yeah, this is the code to run the simulation. I just wanted to give it to you here because at least you have some examples. You just have to take a little bit of time to go through the code and understand the Python. Okay. With that, I'm on time, incredibly, I think. I just want to give you a little bit of references and also discuss further development in terms of demo. So you find a lot of information about the software on Particleworks Europe website. Here you have the papers, public papers we have webinars, recorded webinars, and other content. You can also find us on LinkedIn at Particleworks Europe. Please check our page. We would like to have you follow it because there we post regularly our content and new development on the software. And my email was actually in the first slide. It's here. And please contact me for any question. I just want to mention that, yeah, we can provide demo licensing to you. We can give a 1 month trial license of Particleworks. You just have to contact us, also in my email there. and you have to provide the MAC address of the workstation or the laptop you will use. If you don't know how to extract the MAC address, I can help you with that. So just write me an email.
Yeah, I already added that to the community, Michele. So it should be quite clear. I think you can all send me the MAC address to my email address, and then I'll forward it to Michele. I think that's the most efficient way. And let's probably say we start the trial, I don't know, maybe next week, mid next week, end of next week. So yeah, also would be great if you can send us the slide deck, Michele, and also some additional resources such as tutorials that people can work on.
Yes, once you actually install Particleworks.
Oh, perfect.
So in the help, you have a user manual that can answer most of your questions. You just have to read a little bit through. And if once you install Particleworks, if you go to the file location of installation, so open folder location, we have here some samples, MPS. So actually you have, so it's actually here, you can see that you have tutorials, Particleworks tutorials. So you have different type of examples and a step-by-step workflow to build that example.
Perfect. I think it would be great probably to have a homework for the participants, or at least work through a tutorial once they have a license. That would be great. Cool.
Yes, yes. You could take maybe an example. Yeah, I don't know which one could be the most. I mean, this one could be nice. So gear oil flow. Yeah, you can try to do a step-by-step simulation there. Just one thing, it will refer to some STLs here. And to find those STL, you have to go to samples, MPS, and actually they are hidden in the downloads here. So you have to go to downloads and then check for gear, for instance, gear STL. So it's the only way to find them quite in a fast way. Otherwise, you have to check for every directory.
Perfect.
So I just repeat, this is the directory, installation directory. Then you go doc and English samples MPS, and you have all the what you see here.
I assume, Michele, that you need the Windows to run the program. Mac or Linux doesn't work, I guess, right?
Linux work, Mac it doesn't.
Okay.
So the requirements should be also here. In the doc, you have install guide, maybe. You see Particleworks.
System requirements, probably.
Yeah, exactly.
Okay.
Yeah.
Perfect. Nice. Really cool. I think it would be more than fair if people try the software and then maybe share screenshots or like their renderings on LinkedIn or Twitter, wherever they might be active on.
Yes, it would be nice to promote then, or to use the software for some post on social media, or for some projects that you might have in your either university or industrial workspace. I don't know your background or what you are actively working on, but yeah, it would be nice to apply, if possible, to an example that you might have in mind, and produce some content. Yeah.
Amazing. Any more questions, guys? Put them in the chat. Otherwise, we'll wrap it up. It's the last session for the day. I think we're all a little bit exhausted. But thank you so much, Michele, for the presentation. I think we are seeing you in week 2 or 3, actually 3, sorry, in simulation week.
Yeah,
Yep.
that is correct.
So yeah, really looking forward to that. In the meantime, we'll figure out the issue with the MAC addresses. Yeah, and then you'll have access to Particleworks.
Yes, yes. So let me see if I can find the precise day. I
think
it's the 25th, I think.
25th from 8:30 to 9:30 p.m. Central European time.
Yeah.
Correct. Cool. Really looking forward to it. Thank you so much, Michele. It's quite late, I know.
Yeah.
But thank you so much for doing this.
You're welcome. You're welcome. Thank you.
Thank you, guys.
It was nice
Have a good night.
Meet you. Yeah. Bye.
Bye-bye.